Hi, everybody, and welcome to the Astronomy on Tap Groningen September edition. So I'm Nikki, one of the organizers of the Astronomy on Tap Groningen. And actually, recently we had quite some changes in our organizing committee. So we had some of the organizers that had to leave because, it's actually a good thing because they got new PhD positions. So Vileke, Amit, Marik, and Alex are now gone from our organizing committee, and we wish them all the luck in their new projects. And also we hope to see them soon as one of our speakers. And on that note, we also would like to welcome our new organizing committee member, which is Georg. So yeah, welcome, and let's see what we have prepared for today. So today we have the format that we also had before. So it's two speakers. We have Nikki Arendse and Roy Smits. And during these two talks, we ask you to ask questions like usual. So just ask questions using either comments on this YouTube video, or you can also ask questions using any of the social media. In case you use social media to ask questions, just don't forget to tag us so that we don't miss your question. So during this talks, we will collect your questions, and I will join the speaker after their talk, and I will redirect all of your questions. Then after both of the talks, we have a little break for you to get your beer or relax and prepare for the quiz. And during the quiz, we have one round, which is majority of the questions inside are related to the speaker's talks. So make sure to concentrate, to focus, to listen, and to ask questions. Then after the pub quiz, we also open the live pub, which is actually open from now. So you can also join it right away, and you can follow the speakers' talks from there. You can also join the pub quiz from there. But in the end, it would be very nice if you would join, because you can interact with speakers or with organizers or with other viewers as well. So let's start our September event. The first speaker tonight will be Nikki Androst, and she will, Nikki Arendse, sorry, and she actually did her master's here in Groningen, and now she's at DARC, which is at the University of Copenhagen. So Nikki's research topic is cosmology, which is the science of understanding the origin, evolution, and a large-scale structure of the universe, with the idea of understanding its future. So today, Nikki will talk about the crisis in cosmology that emerged recently and made us question what we know about the universe. So here you go, Nikki.
Thank you. Hi, guys. Okay, so let me share my screen. Yes, okay. So yes, I went from Groningen to Copenhagen, which is not such a big change because I still have a lot of licorice and rain and bicycles, so I feel pretty at home there. And today I will talk to you about my talk, Hubble Trouble. So there's a problem that emerged recently in cosmology, which I'm also working on, and it may point that our understanding of the universe is not as good as we thought it was. But first, to have an idea about the skills that I'm talking about in cosmology, because that's really understanding the large-scale structure of the universe. Let's zoom out a little bit. So we can zoom out from planets to stars to galaxies. And then if we zoom out even further, then all the galaxies are distributed like this. So they're not distributed evenly throughout the universe, but they clump together and they form these sorts of structures, kind of similar to neurons in the brain. And in cosmology, we really try to study these structures and to understand why they turned out this way. We also attempt to go back in time to learn more about the beginning of the universe, and even further in time to see what we can learn about our future. And by doing this, we looked at a lot of data from different telescopes, and we think we've developed a pretty good understanding of the universe. But of course, usually when we think something like this, it's usually about to break down. And there's something today that might be pointing at this as well. So this is called the Hubble tension, and this will be the focus of my talk today. So in this talk, I'll try to answer the following questions. What is the Hubble constant, and what does it tell us about our universe? What are the two ways we can measure it, and how do they work actually? And then we also see how a recent problem might point in the direction of some new physics. So our story starts in 1929, when Edwin Hubble was looking through his telescope at some nearby galaxies. And he looked at these galaxies and calculated their distance to us and also their velocity with respect to us. And what he discovered was that galaxies that are farther away from us are also moving away from us at larger velocities. And this was really an interesting discovery. And if you think that there's nothing special about our place in the universe and that you would observe this effect anywhere else in the universe as well, then this actually points to the conclusion that the universe is not staying constant in size, but it's actually expanding, getting bigger. Now, to understand this interpretation, let's take a look at this grid here of different galaxies. So all the gray points are galaxies, and the blue dot in the middle, let's say this is the Milky Way. And this is just a snapshot of the universe at a certain time. Now, if we go forward in time, and if it's true that the universe is expanding, then in another moment in time, we would see everything like this. So space has expanded and the galaxies are further apart. Now, what would this look like from our perspective, from the Milky Way? If we center these two images on top of each other, then it would look like this. So you see that indeed everything seems to be moving away from us, and also that things that are further away move away faster than things that are close by. Now, and again, let me stress that this is nothing special about our position in the universe. We could do the same thing, for example, for the white dots right next to us and center the images on this, and then you will see exactly the same effect. Now, this discovery that the universe is expanding was incredibly important. For example, it led us to form the hypothesis of the Big Bang, because if you would go back in time, then it means that at some point, everything would be in one place. It also allowed us to calculate the age of the universe. So of course, when we know that it's expanding, the next question to ask is then, okay, but exactly how fast is it expanding? And this is given by the Hubble constant, which is the present day expansion rate of the universe. So how fast is it expanding today? Now, this is named after Edwin Hubble, of course, even though actually Lemaitre was the first one to discover this effect, but he didn't really get the credits for it. Now, there are two independent methods to measure this Hubble constant. The first one is the local method, and this is similar to how Hubble and Lemaitre discovered it as well. So you look at objects around you and then determine their exact distance from us and how fast they're moving away from us. And then you combine this, it gives you information about how fast the universe is expanding. And then I say local objects, what exactly are those? Well, there's a lot of different probes that we can use in astronomy to determine distances. We mostly like to use standard candles, which are objects of which we know their true intrinsic brightness. So if we know how bright an object is, and we observe it a lot fainter, then it must be further away. So by determining how faint it is, we can also see how far away it must be. An example of this are Cepheids, which are stars that fluctuate in their brightness, so they become brighter and dimmer. Edwin Hubble also used those to determine his distances. But now, of course, we have a lot better and more expensive telescopes, so we can look a lot further out into the universe. And this allows us to also use objects called supernovas. So these are exploding stars at the end of their lives. And especially this one type, the type 1a, are very useful because they always explode when they have the same mass, so the same luminosity. And then if we look even further into the universe, we can find ways to use these extreme objects called quasars, which are supermassive black holes at the center of galaxies that eat the gas around them and then emit jets of light. And these objects are super bright, so they can be seen until really far away. And these are just a few of the objects we use, and we're always on the lookout to find ways to use more objects to determine distances. Now, putting this all together, what does it give us for the expansion rate? When Hubble did it, he came up with a number of 500. And if you're curious about these units, kilometers per second is a velocity, and megaparsecs is a distance measurement. And we use this in astronomy because galaxies are so far away. So 1 megaparsec is around 3 million light years. So this just means that per megaparsec, galaxies are moving away from us with 500 kilometers per second. But now actually we know that this measurement of Hubble was pretty far off. And the most recent measurements The most precise one we have gives us 74.0. And this is carried out by the SHOES team using the Cepheids and the supernovas. And there have also been other teams with different measurements. But for this talk, we'll work with this one because it's the most precise value. Now here you have a timeline of the universe, where on the left you see the Big Bang, and then the universe expands and it forms stars and galaxies. Then at the right, this is where we are with the observer eye. And the method that I just described is called the local method, because we look out from our own galaxy into the universe and use the objects we see there. Now, the second method that I want to discuss is different because it looks back into the universe almost all the way to the beginning. Now, that's a pretty strong statement. How can you look back to the beginning of the universe? Well, as astronomers, we're pretty lucky that light travels at a finite speed. So even though it doesn't seem like that in everyday life, it takes some time to travel from one point to another. So the moon, for example, is 1 light second away. And the sun is 8 light minutes away. So it means that if we look at the sun, we don't see it as it is now, but we see it as it was 8 minutes ago. And this is maybe not such a big difference. I mean, okay, 8 minutes, but remember that this applies to everything in the universe. So if we look at very distant objects, we really see them the way that they looked in the past. And this can be really useful for us. So if we look as far as we can back in time, then we see the first radiation, so the first light that we can see. It looks like this. And this is called the cosmic microwave background radiation, or in short, which I will use is the CMB. And this is thought to be an afterglow from the Big Bang. Now, this picture is really famous in astronomy because it's really useful. We can determine a lot of physics from it. For example, if we look at the properties of this light, like the temperature, then the temperature is very homogeneous everywhere. So almost the same temperature, but not exactly. There are some slight variations. These variations are very small, kind of compared to a very little insect next to the Martini Tower in Groningen, but nonetheless, they're there and we can observe them. So in this image, they correspond to the different colored patches, where the dark blue regions correspond to cold spots, and these are formed by overdense regions in the early universe. And the red spots correspond to warm patches corresponding to underdensities. Now, this is a snapshot of the beginning of the universe, and as it developed under gravity in time, then these dark blue dense regions turned out to form galaxy structures and other heavy structures, and the red regions, they developed into the voids. So in this way, the cosmic microwave background radiation really contains all the seeds for the structures that we see around us today. And this is really cool, and I think actually the CMB can deserve a whole talk by itself. But for now, let's not get too distracted and go back to our mission, which is to calculate the Hubble constant. How can we do that using the CMB? Well, first we can measure the size of the fluctuations, so these blue and red dots. And if we combine that with some knowledge of the early universe, then this can give us a measure of the expansion rate at that time, so at the CMB. But of course, what we're interested in is the expansion rate today, the Hubble constant. So we need something to go from one to the other. And for this, we use our best knowledge of the expansion of the universe, our best cosmological model. Combining this will give us the Hubble constant, the present day expansion rate. Now, so you might already think that there's quite a lot of assumptions here at play, and this is important to underline. It's really a measurement of the properties at the CMB in combination with our best cosmological model to move those forward in time to get the present day expansion rate. So let's have a look at what this best cosmological model is then, because it's pretty important for the determination of the Hubble constant. So let me introduce to you lambda CDM, where this first part, lambda, is the Greek letter, and this stands for dark energy. So this is a mysterious energy that drives the expansion of the universe, and it makes up about 73% of our universe. Now, I say mysterious because we really have no idea what it is. And then the second part, CDM, stands for cold dark matter. And this is invisible matter that likes to hang out around galaxies. And it makes up about 23% of our universe. And about this, we also don't know what it is. And we're constantly trying to build bigger and more expensive experiments to find out, but so far, no luck. So what about the remaining 4% then? Yes, so that's all the ordinary matter. So you, me, and everything you see around us. And then the last ingredient for this model is Einstein's theory of gravity. Okay, so what exactly does Einstein have to do with this model? Well, all the things I mentioned, the dark energy, dark matter, and the ordinary matter, they're all the components of the universe. And how they evolve over time and then interplay together to form structures, this is all determined by gravity. And our best theory that we have of gravity is Einstein's theory of general relativity. So this is the one that we use in the model. And also a little fun fact, Einstein was actually the first one to come up with the term lambda in his equations. But at the time, he thought he was wrong, and he called it the biggest blunder of his life. And then 80 years later, observations actually proved that he was right after all. It's pretty cool, but I guess he's mostly right. So let's go back. Now that we know a little bit more about this cosmological model that we use, we can combine it with measurements from the CMB to get the expansion rate today. Now, if we do that, we get a value of 67.4. And let's compare that to what we got from the local measurements, which is 74.0. So you see that these numbers, they're not the same. And of course, they both have some uncertainties, but that cannot explain the difference. And this problem is also known as the Hubble tension. And remember that both of these, they're really trying to measure the same number, the expansion rate today. So they should give the same outcome. So something is wrong here. And also to illustrate that it is actually an important difference, you can calculate the age of the universe with the Hubble constant. And if you take the one from the CMB, this will give you an age of around 13.8 billion years. But then if you calculate it with the local measurement, this will give you like 12.7 billion years. So there's a difference in age of 1 billion years, which is a long time. So I think it's quite important. Okay, so what could be going on here? If we go back to everything that we talked about so far, so we have the CMB measurements, cosmological model, and the local measurements, then roughly speaking, there are 3 options to explain this difference. Either there's a mistake in the CMB measurements, or there's a mistake in the local measurements, or something is wrong with our cosmological model. And this is, of course, by far the most exciting option, because then it means that we need some new physics beyond our lambda CDM model. And this really opens the door for everyone to speculate and become creative and come up with their own favorite explanation for this tension. So let me give you a few examples of those solutions. So what, for example, if the dark energy density is not constant over time, but it's actually increasing? This would lead to more accelerated expansion. Or what about, what do we actually know about what was there before the cosmic microwave background radiation? And what if we add some exotic new particles there? Then this would change the predictions that we get from the CMB and also change the Hubble constant. Or perhaps even more extreme, what if Einstein was wrong? What if we need a new theory of gravity beyond the theory of general relativity? Now, these are a lot of models, and part of my research is also to investigate these models and to test if they actually work or not. And I think it's pretty cool and fascinating to work on this, because most of these models also have some consequences for us, for the future of the universe. So for example, the first one, increasing dark energy density over time. This would mean that the expansion would increase, and it would increase so much that in the future, at some point, it would rip everything apart. So galaxies, planets, even atoms. And this scenario is also called the Big Rip. So that's one possible scary future for us. But don't worry, the timescales are really immense. So this would be like tens of billions of years. I think we first have to focus on fixing coronavirus and global warming. And possibly a bit closer to home, what if we need some refinement in Einstein's theory of gravity? This would have consequences for us because we use general relativity in daily life as well. For example, the satellites rely on it, And we also use it for precision timekeeping on Earth. So that would actually mean something for us. Okay, so to conclude, the Hubble constant is the present-day expansion rate of the universe. And it can learn us a lot about the past of the universe. We can use it to calculate its age, and it can make predictions about the future. There are two ways that we can measure its value. The first one is by using local probes like Cepheids, supernovae, and possibly quasars. And the second one is to use the cosmic microwave background radiation in combination with our best cosmological model. Now, these two methods give us different outcomes. This is a problem in cosmology, and it may point at that we need some new physics beyond our current cosmological model. So a lot of different models have been proposed, and hopefully some future data and better observations will prove those models right or wrong. But for now, we can all speculate and have fun. Thank you.
Thank you, Nikki. I don't know. I don't see myself, but maybe yeah, I'm heard. So yeah, we'll just continue. But bravo. It was very nice. I think it's a very cool talk because you often get these kinds of questions because people hear that the universe is expanding. But I think it's very hard to kind of visualize how that is actually going on. So I think it was very nice to have this little image you showed, kind of that if you look from our point of view, this is how it will expand, but it's the same for our neighbors and everybody else. But it's also, so one of the questions, for example, that I get when talking about this expansion of the universe is, how come that if everything is expanding, how come that then we can still, for example, see mergers of galaxies or mergers of certain structures?
Yeah, that's a good question. So in general, everything is expanding, but the expansion is not so strong. So if things are close together, then gravity can actually overcome the expansion. This is why, locally in our galaxy, we don't notice the expansion. We still see gravity at work. And also here on planet Earth, of course, we also don't notice the expansion. And if two galaxies are close together, they can also have so much gravity acting on each other that it dominates over the expansion of the universe. So you can still have these phenomena.
Yeah, it's very nice. And I mean, it would be nice if somebody is interested, they can have a look at the simulations of mergers. It also looks very cool, but probably there is some also simulation of this expansion that maybe we can provide later in some links or something.
Oh yeah, I don't know actually.
We'll manage to find something. But also, so I wanted to ask you, since there are these two Hubble constants, right, that were measured. So for example, we use this constant for a lot of calculations. So for example, which one would you recommend to be used?
That's a good question. So I would recommend using 70, like somewhere in the middle, just to But if you want my personal opinion about which one is probably right, I would lean more towards the value from the CMB. Just because, so we tested some of these models and they don't really seem to give a good explanation for the difference. So I would say that it's probably not new physics. And there also have been some measurements of the local method that don't completely agree with each other. So that's a bit suspicious that, within the local measurements, there's still some tension. So I think that there's still some things that we need to figure out about the local measurements because it's just very difficult to do. So I would say that, yeah, I would put my bet on the CMB one, but that's just personal opinion and might change over time.
Okay, that's, also nice. You work on it, so it's a valuable opinion. So we have a question. Can universe keep expanding unlimitedly? I don't know if that's a proper word to use, but yeah, is there a limit that is predicted? Is there like a prediction of stopping of this expansion?
No, there's no prediction. Like, of course, there are different scenarios, so we don't know exactly how the future will unfold. One of the scenarios I talked about is the big rip, that the expansion will increase so much that it tears everything apart. The explanation that is the most probable with what we know now is kind of the heat death. So it will keep expanding forever and forever, and slowly everything will kind of cool down. It won't be ripped apart, but it will just kind of expand forever, and at some point there's just not much left. And there's another scenario, which is the big crunch, that at some point this expansion might be reversed, and then we would go back to to decreasing size. But there's not really any evidence for that. Like, it's a cool theory, but we haven't really discovered anything that points towards the fact that at some point this expansion would change and then suddenly reverse.
Yeah, we're still trying to figure it out. I mean, the first part.
Yeah.
Yeah, so we also, okay, this was, we kind of answered, but I had one that was, yeah, interesting. So you're talking about cold dark matter, but does cold mean a cold temperature, as the universe is very cold?
Yeah, cold means that it doesn't have a lot of velocity. But there have also been some models for warm dark matter, and then it has some more velocity. And this kind of changes how it forms structures. So if it has more velocity, then it's less affected by gravity, for example. So then the structures that you see, if you run a simulation, they create a slightly different prediction of the structure in the universe. So we compared those simulations to what we actually see around us. And then it turned out that cold dark matter was the most, gave the best predictions.
Okay. And we have, yeah, I will read one more. So can the differences in the measurement of the local Hubble constant come from the fact that we are on the edge of a huge void?
Yeah, there's some speculations about that, but probably not, because when we say local, like maybe we used to use sources that were so local that they could be affected by this void. But now we look so far into the universe that we use sources at redshift of 1 or 2, and that's probably further than the influence of the void.
Okay, so anyways, should be fine.
Yeah.
Okay, thank you, Nikki. We have more questions, but now we'll go to our next speaker. So if I didn't read your question by any chance, you can always join us in the live pub that we have and ask Nikki directly. But yeah, thank you, Nikki. It was very nice.
Thank you.
So as our next speaker, we have Roy Smits. So Roy Smits did his PhD in Nijmegen, and after that he worked at the University of Manchester and as well as Astronomy, which is very close to Groningen. So he has done a lot of scientific projects, but he has done the groundwork for the pulsar research with the Square Kilometer Array. I think we covered both of those topics so far in our Astronomy on Tap talks, but if you're more curious about this, you can always ask Roy later. And more recently, he has helped build ARTS, which is a new backend for the Westerberg telescope, which is also very close to Groningen, so you can probably also go and visit it. It's very interesting site. And on top of all of this, so he is also doing the communication, so the outreach, so communication with the general public, and he has published recently a new book that is called, now, yeah, good luck to me. So Telescopen and Tijdmachines, which is telescopes and time machines.
Yes.
So today he will talk about the event that happened in 2007 when astronomers saw a radio flash coming from seemingly from out of nowhere. So today we will find out, was it real? Was it human-made? What was going on? So here you go, Roy.
Exactly. Thank you very much for the introduction. Yes, my background is pulsars, and this talk is a little bit pulsar related because the signals we're seeing are very similar. And I will talk all about that. Let me see if I can share it. There we go. Okay, so my talk is titled Radio Flash Out of the Void. And it's a bit of a story that I'm going to tell. And the story begins with the most beautiful telescope in the whole world, which is the Parkes telescope. It sits in Australia near a village called Parkes. That's why it's called the Parkes telescope. There's actually a whole movie made around this telescope. It's called The Dish. I can really recommend it. It's beautiful. So the Parkes telescope sits in the southern hemisphere where it can see the southern sky, which is valuable because we cannot see that from the Netherlands or most places where we have radio telescopes. And this telescope is very suitable for finding those objects that I've studied called pulsars, because it has a very large surface area, but also because the hardware is perfectly engineered to find those pulsars. Particularly, you need a high time resolution for that. And I'll tell you a little bit what pulsars are. I can spend ages talking about this. I'll keep this very brief. So in the center of the pulsar, you have a star called a neutron star. And it's a very compact, small star, only like 20 kilometers in diameter, which in astronomical measures is incredibly small. It has tremendous strong magnetic field, which is illustrated here with these curves. And it emits radio waves in a beam at both magnetic poles. and the whole thing rotates around an axis. So this beam rotates along as well. And if this beam points towards the Earth, then it works like a lighthouse. Lighthouse, when it has a light that rotates and it points towards you, you see a flash of light, and then it's gone again, and then it comes back. And this pulsar does exactly the same thing, but then with radio emission. So this beam rotates, and when it points towards the Earth, you see a flash of radio emission, and it only lasts a few milliseconds. That's why you really need a special kind of processing of your data to be able to see this. And to find pulsars, we use a special algorithm because these signals are very repetitive, right? These things rotate several times per second. So the signal comes back several times a second. It's perfectly periodic. So we have a mathematical algorithm, it's called the Fourier transform, which is pretty much just magic. And it just gives us this periodicity out of the data. A computer can do that for us. But then, some time ago, publication was in 2006, a Nature publication, people found that you shouldn't just have computers looking at these signals because you might miss a few things. And what people found was what they called RRADs, rotating radio transients. So people looked at the single pulses of this data. And what you see here is on the x-axis time, and on the y-axis is a variable called dispersion measure. Now I'll explain later what that is, but for now you can just picture that dispersion measure tells you the distance to the source. And here all these dots are just sort of the intensity, what you see in this plot, and most of it is just noise. But sometimes if you look at this plot by eye, without using a computer, you can see these single pulses. And it repeats at the same dispersion measure, at the same distance. So these pulses come from the same source. Now, if you just look at periodicities, you would miss this. So this tells you don't always trust computers to do all the work. If you want to make new discoveries, you got to find new ways of looking at your data. And sometimes you still need the human eye. And this was a tremendous discovery. It's called RADS, and we're still studying these objects. Here they have 3 different parts of the observation. 3 times you see this repetition of a signal, which is a RAD. And we now know that these signals come from objects that are pretty much the same as pulsars. They also have a neutron star, but they have even stronger magnetic fields. They're called a magnetar. And the emission from a magnetar is similar from a pulsar, but it's not a constant emission. The emission is much more erratic, so it sort of have little bursts of emission. So that's different. A pulsar, you see pulses because there's a constant emission, but it rotates. So it leaves the line of sight, and then it comes back again. But in a RRAD, it actually intermits. So you have little bursts of emissions of a few milliseconds. So that was a big discovery they made. And then a year later, one of the co-authors, Duncan Lorimer, he had a student, David Narkevich, looking at this data, and he found an extraordinary burst in this data. And I don't have the original plot he looked at. I do have the data, I'll show you in a bit. But what he saw was very similar to this. One huge burst, brighter than anything they've ever seen. It actually so bright, it saturated the antenna of the telescope. And the DM value was tremendously high. It was an extraordinary burst that he saw. So together with Duncan Lorimer, he looked at the data, he sort of zoomed in on that pulse, and he looked at the data in a different way. So here I actually have the data, and I did the same analysis. What you see here is that unique burst that became known as the Lorimer burst. And you see here time, this is actually milliseconds, and frequency. So you know when you listen to a radio, right, and you want to change the channel, you change the frequency you listen to. So you change the channel. But astronomers, we're greedy. We want to see all the radio channels all at once. So we record all of them. So when we find something, we can go back and see all the radio channels. That's what's plotted here. The time behavior of each radio channel. And this data is a bit remarkable because it's only 1-bit data. It's just ones and zeros, and white means a high signal and black means a low signal. You can ignore the black horizontal lines. That's just data that's been zapped because it was bad data. And you see these two curves here, these two black lines. That's just to guide the eye at the white signal in between. If you look at that, it's all white. This is maximum signal and possibly many times more brighter. So it saturated the antenna. That's how bright this was. And you might notice that the signal is a bit curved. The width, by the way, is also a few milliseconds. So it's very similar to a pulsar. And that tells us a little bit about the source. If something is a few milliseconds long, then if you think about the light travel time in that time, it can only travel a few tens of kilometers. So that means that the source must have been very small, like, for example, a pulsar, but we don't know that in this case. All we see is this one off burst. It didn't repeat, it's just one burst, and it has this curve in it as a function of frequency. Now that curve we can understand because when a radio signal travels through space, it actually gets a small delay. We call that dispersion. What happens is that space isn't just a vacuum, it has protons and electrons in them. And especially those electrons, they interact with the radio waves and it causes a delay. And that delay is dependent on the frequency of that wave. That means that a high frequency gets a little bit delayed and a low frequency gets a larger delay. By the way, the units here are gigahertz, in case you're wondering. So the top frequency arrives before the lower frequencies. That's why you see this sort of dispersion happening. And it's not a straight line because it's not a linear process. It actually turns out, if you do the physics, is that the time delay depends on the square of the frequency. So it's a quadratic relationship. That's why this line is also a little bit curved. And it follows that quadratic line perfectly. So this looks like a real signal from space. Now there's one neat thing that you can do when you measure this delay, when you measure the dispersion, and that's what's been done in this previous plot. This is the DM. I told you that's a dispersion measure. And it sort of tells you how many electrons the radio wave passed from its source to the Earth. And if you have a little bit of an idea what the density is of the electrons in our galaxy, and we think we do, then you can translate that dispersion measure to a distance. And that's what they did for this curve as well. Except when you do that, it turns out that if you look at the direction where the source came from, and you look at the dispersion measure, then it came from beyond our galaxy. It didn't come from inside, but outside our galaxy. And that's remarkable because all the signals that we see that are like this are all nearby at a few hundred light years distance. That's what we call our backyard. That's close by. But this came from far further than that, outside our galaxy. That's remarkable because it's incredibly bright. But there's nothing there. If you go outside the galaxy in the direction where this burst came from, it's the void. There's nothing there, just empty space. So where did this come from? And that's of course very unsettling when you see a burst this bright and it comes from nowhere. And one thing you can think about is like, well, maybe it came from much further because we don't know the electron density outside our galaxy. We know it's very low, so it could have come from very far away. And maybe if you go really far away, the first galaxy where it could come from is at a distance of a few 100 million light years. So that is an astonishing distance. Remember, typically we see these things from a few 100 light years, but if this came from the nearest galaxy in that direction, it must have come from 100 million light, a million times further away. But if it's a million times further away, the source is also much, then you would expect that the intensity of what you're seeing is much weaker because if I would put something, a source, like if I have a light bulb, and I would have put light bulb 10 times further away, then the intensity of the light bulb drops by a factor of 100. It's also goes with the square of the distance. So again, let me just repeat that. If you have a light bulb and you see the brightness of it, and you put it 10 times further away, the intensity of the light, the way I see it, goes down by a factor of 100. And that means, considering that we saw this very, very bright burst at a distance of a million times further than normal objects, that would mean that the intrinsic brightness of that object would have been a million times as strong as a normal object that we see here. And that is just astonishing, so hard to believe. But then again, if it didn't come from so far, it must have come from the void. There's nothing there. So what is this? It's such a crazy contradiction that people started thinking, this is not from space. Come on, we just saw this once. And people were criticizing the data. It's just 1-bit data. We saw this, a one-off event. We never see it again. This is not real. This is some local interference. And the people who claimed that, they got a little present. Because another student, Sarah Burke, started looking at the same data set, and she found these signals in the data. She called these Paratons. It's named after a mythological creature. I can recommend that you look that up. And what you see here, I hope you can see that at your side as well, but there's a very weak signal in this data set. So again, we have time versus frequency, and there's a very weak sign of saying, but there's definitely a signal in there. And what I did is I actually fitted the same dispersion law that you expect from a signal from space to this Paraton. And you see it's a bad match. You can see the signal comes from here, it curves very sharply, then it becomes almost straight, and then there's a bit of a curve again. This does not obey that perfect quadratic law. And again, this is a few milliseconds, so it is very similar to this Lorimer burst. But this did not come from space. This must have been some unknown local interference, some radio burst from nearby. So when people saw this, a lot of people said, well, that's it. This Lorimer burst is simply a Paraton, except it happens to be a very bright one, and it just happens to follow this quadratic law. And so this Lorimer burst was named, of course, after the supervisor of the student who discovered this. So now people are thinking, this is not real. It is a Paraton. It's a simple, all you have to do is find out where these Paratons come from, and the whole mystery is solved. I was there at the time when we were discussing these things in Perth at the Curtin University, and I asked a very simple question. Well, if the Lorimer burst is a Paraton, then what are the odds that it just happens to follow this perfect quadratic law? And nobody had the answer because nobody looked into that. So I did the analysis myself, and I won't show you all the details because it's a bit technical. But what I practically did was let the computer calculate what that value for the power law is. And that's what's plotted here. This is the exponential value for the power law. So that means if it would be 1, that curve would be a straight line. And if that value is 2, then it would follow exactly the curve that we would expect from a dispersed signal from space. So there are no assumptions that go in this plot. And this, what you see here, is the goodness, how well it fits the data. So there's no assumptions that go into this plot. And the computer just tells me that the best fit is exactly 2. And I did a little fit to the top curves to confirm that the maximum is indeed lies at 2, and also to get an error margin. And it turns out that this Lorimer burst, this burst, follows exactly the quadratic law with an accuracy of 99.5%. So to me, that cannot be a coincidence. And also it's much brighter than one of these Paratons. It really looks different. So I also did the same analysis with a Paraton itself, with all of the Paratons. They discovered like 18 of those initially. And I did the same analysis, and this is all over the place. There's no clear value for the power exponent, which makes sense because it doesn't follow a beautiful line. This could be from 1 all the way to 3. So the odds that a Lorimer burst would be a Paraton, they're in the order of 0.5%. It's really very unlikely that they are Paratons, which means they probably still come from space. So I shared these results with Duncan Lorimer. We started working on a nice publication for this. And then some very pesky astronomers, they discovered another one of those Lorimer bursts. Except this one was discovered with the Arecibo telescope, and it definitely came from space. And then they discovered it with the Green Bank telescope, and then they discovered it with any major telescope in the whole world. And by now we found hundreds of these kinds of Lorimer bursts, and they're now called fast radio bursts. So publishing this result is a bit redundant, showing that this is a perfect quadratic law, because people will just say, yes, we know, we found hundreds of these things. So that's a sad thing, but at least we now have confirmation that these things are real. And the big question, so they're called fast radio bursts, FRBs. And the big question now is then, what are they? Where do they come from? We still have this mystery now. And that is what we're working on. And it's a fantastic mystery to solve. So do they come from the void, from the vacuum, where we think there's nothing there? Or do they come from very far away from galaxies, and are they intrinsically incredibly bright? Well, we found a few clues. So first of all, we know there are a few milliseconds in duration. So it means the source has to be very compact. And people did find that one burst came from within our own galaxy, and it was associated with a magnetar. So that suggests that maybe these bursts are very similar to these arrets that I showed. And it's just a very bright version of that. But we don't know for sure. And this was not a very bright FRB. So we don't know if this is true for all FRBs. One FRB was possibly associated with a gamma ray burst. So maybe there's different sources for these tremendous bursts. But we have discovered 2 years ago an association with a galaxy. We managed to confirm that one of those FRBs came from a galaxy. And that galaxy, sit down, that galaxy sat on a distance of 3 billion light years. And that is just absolutely mind-boggling. We got a signal so bright, brighter than anything we see locally, and it came from a distance of 3 billion light years. So something extraordinary is happening at those distances, and we still don't know what that is. We did find that some of these bursts are actually repeating. So that's also a clue that maybe it is related with a pulsar or a magnetar. But again, we're still trying to figure out, this is work in progress. This is one of the reasons that as the Westerbork, we now have these new receivers at the Westerbork telescope called Appertief. They have a very large field of view, so they can very easily detect these fast radio bursts, and they have a special hardware system, a backend, that's the ART system that was mentioned that I've helped build. And that's a fantastic system because it consists of 200 of the very fastest video cards that are used for computer gaming, and we use that for finding these fast radio bursts. So this is work in progress, and very soon I think we're going to find out what these things are. Now that's the story of the fast radio burst, and maybe if I have time left, people might be interested to find out what happened to those Paratons. So since nobody's complaining, yes, I see a thumbs up. Let me tell you, because that's also a fun little story. Maybe I can just go back to those briefly. So this is the plot of the Paratons. So what are these things that we know they're not from space because the curve doesn't follow a quadratic behavior? Now the student that worked on this, Sarah Burke, was speculating that maybe this is lightning. that lightning causes radio waves somehow conducting and causing this nice curve. And she tried to gather data in the time around 2001, that's 2001 data, when this burst was observed. But she found it's actually very expensive to get that data about lightning, because the reason is that insurance companies want that data. It's very valuable to them. And since it's worth a lot of money to them, that means everybody will have to pay money to get that data. It's a bit of a pity, and they didn't have the budget to follow up on that. So she never managed to find the source that way, which is a pity. But somebody else was smart enough to say, well, you know what we should do if this is local, at least what we can do is search the area around the Parkes telescope, see if there's a source of radio interference there. They did search and they found something. The Parkes telescope is a beautiful site, and a lot of people believe that. That's why they put a visitor center there. A lot of people like to come there. The visitor center has a nice little cafeteria where you can have a nice warm drink and a warm snack. And the warm snack they heat up in a microwave oven. Yes, they emit radio waves, and people are not stupid. They know microwave ovens emit radio waves. So what they did is they put the microwave oven, what they call a Faraday cage. It's a metal cage from which no radio waves can escape, just to take away all the interference. But some people working in that cafeteria were a little bit impatient. So when they were heating up some food for the customers, they would open up the cage, open up the microwave oven before it hits zero. And two things happen when you do that. As soon as you open the door, you break the Faraday cage, so radio waves can escape. And at the same time, when you open the door of a microwave oven, it shuts down instantly. It takes about a few milliseconds. And the fun thing is that it turns out that the highest frequencies shut down before the low frequencies do. And that causes a little curve if you would look at that in the plot that we're looking at. So that microwave oven is exactly what causes this curve, which looks remarkably much like a signal that's coming from space. And of course, we have been bothered by this for some time, but at least finally we found out the source of these Paratons. And very soon, I'm very confident we're also going to find out the source of these FRBs. Okay, thank you very much.
Thank you. It was very nice talk. And actually, I mean, I give it thumbs up because that would be my question, because I heard that they were only discovered in Parkes telescope. But at one point, you also mentioned other telescopes. But yeah, probably I misunderstood there. And I heard that it was this premature, I mean, oven opening, microwave opening. Actually, it's very interesting how much we can meddle with our own, yeah, signals. But it's also, yeah, I also really liked, yeah, sorry for this, but it's because it's very hard sometimes, I think, for astronomers to present their work. And I really appreciated your description of the plots that you had, because I think we look at them so often that it's sometimes hard to think that maybe something is not obvious. But I think it was really well done. So yeah, bravo.
Thank you.
It was very nice. So yeah, on top of this question, whether they are real or human-made. So we also got the question, what is Periton? So I'm not really sure if this question refers to the original, because yeah, no, I mean, now we know it's a microwave signal,
but it's also a mythological animal. Yeah.
Yes, so I also actually wanted to open the image.
Oh, there it is. It's beautiful.
In case that was the question.
It's a scary animal. It casts the shadow of a man until it kills a man.
Yeah, not really. So yeah, and we have the question why the signal is called after them.
Yeah, I actually don't exactly know, but it's of course, I think it's a bit of a mystery. And I think it was Sarah Burke herself that came up with the name. I think she just had a fascination with mythological creatures, and she thought she wanted to give it a nice, mysterious name.
Ah, because I thought since it's kind of like a mixture of two animals, right, in a way?
True,
I
yes, absolutely.
Maybe because it follows that follows the curve, but then kind of also changes. I mean, this is also my opinion. It's really
your guess is as good as mine. Could very well be true. Yes.
We have to ask the original.
We can, yeah.
So the second one is, can the signal come from aliens? So I will rephrase a bit, maybe, just since we saw this microwave origin. So, like, how can, for example, people know if a signal comes from the aliens? Is there a way to determine, like, from example, what they do with SETI? So how do they determine if it's human-made outside of our galaxy?
Yeah, so that's of course very difficult. Every time radio astronomers find a signal that they don't know what it is, the SETI people will jump in and say, oh, it's aliens. But so the first thing, if it's aliens, the first thing it needs to be is nothing else, right? It cannot be a natural phenomenon. So it cannot be a pulsar or a gamma ray burst. It has to be something that we don't know. And that happens sometimes, especially with these FRBs, something like, well, we don't know. Well, then it could be aliens. But then, of course, if you want to confirm it's from aliens, it needs to have some signature of intelligence in there. It has to make sense also. And we did that when we first found the pulsars, because it's so beautiful periodic. And I didn't mention, but the periodicity of pulsars is as good as an atomic clock. And nothing in nature that we knew about before pulsars is that accurate. We had to invent atomic clocks to get that accuracy. So that's a sign of intelligence. So when you see a signal from space that's that beautiful periodic, then you start to think, yes, this is intelligent life out there. But as it turned out, no, it's not. It is a natural phenomena. And we do understand how this is possible. It has to do with the fact that the star is incredibly dense. That's why it's so very periodic. As for the fast radio bursts, there's no sign of intelligence in that. It looks exactly like a very natural phenomena. The only remarkable thing about it is the incredible brightness of it. And that is so bright that it's very hard to imagine alien life doing this for no reason, right? It's like, why would you? I mean, it's like the energy of not an entire star, but very close to a big chunk of matter, huge amount of matter. Maybe, I'm not sure about the numbers, but maybe like a whole moon getting converted into energy at one time. You know, why would aliens waste such a precious resource? So it's much more likely to be some sort of very extraordinary event that we do see in nature. We see like a gamma ray burst or like the merger of black holes, things like that. Yes, tremendous energetic events. That makes sense because there's so much energy involved here, and of course a very rare event that will make sense to originate. And also we see these fast radio bursts from all over the sky, right? And that would be very weird because if there's aliens over there doing this, for some reason there's also aliens over there doing exactly the same thing. That doesn't make any sense. So when things don't make sense, we say, no, it's probably not aliens then.
Actually, there is one question also regarding this. So basically asking, how are the fast radio bursts distributed over the sky?
Uniform. That's the remarkable thing. If it would be local from a galaxy, you would see it follows the galactic plane. But it's not. It's pretty uniform. So it really is from a random location. That's typical from when it's beyond our galaxy. Then it's like what can come from literally anywhere.
And it also, so question regarding this is also, can it tell us something about their possible origin, their distribution?
Yes. Oh, the distribution.
Them or.
Well, like I said, it confirms, of course, it's extragalactic. But apart from that, you have to see for every burst itself if you can find the origin point, which we did a few times, found the galaxy where it came from. But the distribution itself, it just tells us it's clearly coming from galaxies far, far away.
Okay. And also, so one more thing is that, so since we're talking about these human-made, alien-made signals as well at this point, and we have this radio data, right? So in radio data, we have, as you said, microwaves, for example, producing signal that we might as well interpret as something coming out from space, actually. So if you can just explain briefly, how do people deal with this? Because we also have a lot of satellites right around us. So how can we know what is real in the radio data that we get?
This is a nightmare.
Yes,
this is the one thing, radio astronomy has its perks because a lot of things are very easy, but this is the nightmare of radio astronomers, all the interference. It is really, really bad. There's a couple of frequencies that are clear that nobody's allowed to transmit on, to keep it clear for astronomers. But that's getting narrower and narrower because radio frequency gets expensive. So it's hard to keep that free. Then there's airplanes. They have special collision systems. You know, you got satellite. You got Elon Musk setting up a whole communication system in space. Google is doing it with balloons. It's an absolute. There's mobile phones everywhere. Okay, so the way to deal with that. First of all, build your telescopes not in Drenthe anymore, not in the heart of the Netherlands somewhere, or in the heart of anywhere in Europe. Put them in the desert. That's the best place to get it RFI free. But also what we can do is these days we build telescopes not as one big telescope like you saw with Parkes, but lots of small dishes, lots of small elements, like Westerbork, also LOFA, if you're familiar with that, lots of small elements. And if there's a local interference, it'll show up differently in the little elements. And that means you can distinguish them from sources very far away because it has a different signature. So there are tricks that we can do to try to avoid it, but it really is a nightmare. We keep fighting against this RFI, as we call it.
Yeah. So any potential space lawyers out there?
Well, there are some legal aspects to this as well. There are some legal cases going on. Yeah, it's a very difficult to keep that space free for radio astronomers.
Yes, but luckily, yeah, some of the frequencies also we know which are affected. So yeah, there are ways to deal with it.
Exactly. Yes.
Sadly, a bit harder, but.
Can I just tell a little funny story about that? Because in Westerbork we have one frequency channel. What is the 600 megahertz? We used to use that for wonderful science, and then somebody built a radio antenna near Smilde that is broadcasting digital television at that exactly frequency, and we never managed to use that frequency again. It's just completely saturated antenna. It's useless because of that. Then a few years ago, by chance, there was a fire in the emitter, and we had nothing to do with it. We completely denied all responsibility. But for several days, we had the perfect sky at that frequency. It was so beautiful to watch. They did have to restore the antenna, but
yeah, I mean, astronomers are not bad people. They just really like when they can observe.
We do have what is it called, Schadenfreude.
Yeah. But yeah, thank you very much, Roy. So now we will continue with our program. So now we will just relax a bit. There were more questions, but we cannot discuss them all. So yeah, please, all of our viewers, join us later in the live pod, or you can also do it now and actually do the whole quiz from the live pod. So I will leave you now, and Jake will take over with preparing you for joining Kahoot. Thank you.
Thank you very much.
Yeah, thanks to both speakers. I have to say a story. When I was a first-year undergrad, that my project was building this microwave Fresnel lens antenna that could detect these signals. And at that point in time, one person had a cell phone on campus, and we could tell whether she had it switched on or not from our telescope. Anyway, next we move into our quiz, and I'm just going to share with you the joining link. It's in Kahoot as usual. Please join as soon as you can, and in 4 minutes time we will start the quiz. So I will just now share you the screen if I can still do it, and then please join the quiz. We have 3 rounds today of 4 questions each. So we hope you'll join us. Also, you can find the link to join the Zoom pub, so you can do the quiz there and get help from other people if they're unsubtle about the answers, or you can stay here and do it on YouTube live too. Here is the Kahoot, so please join. 2 minutes and we'll start the quiz. Join now. One minute to go and we're starting the quiz. Oh man, Jesus has joined. Impressive. Anyone else who wants to join, I'm giving you like 30 more seconds. Solid nickname. Gagarin. Good to see you. Just 3D printed your head. All right, we're starting in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So we know the delay right now is about 2 seconds or 3 seconds, so please answer fast. In what year did Edwin Hubble first calculate the Hubble constant? Already right in with the question. 1915, 1921, 1929, or 1936? Quicker the answer, the more points you get. More points you get, more prizes you get. Points and prizes. And if you're too slow, it'll end before you even know it. Yeah, 1929 is correct. Well done, those of you. 1921, popular choice. 1920s for sure. All right. Remembering that there's about a 2-second delay, we think, between when I'm giving you the question and when you can answer on the phone. So you'll see the answer 2 seconds before I say it, and then at the end, you better answer 2 seconds before you think the time is ending. So here we go with question 2. Oh, no, I always forget the scoreboard. Oh, Leiden in the lead, slightly in the lead. Peritons second, nickname third. Zeus, Lucia doing well. Jesus not on the scoreboard yet. All right, here we go. Which probe is not used for the local measurement of the Hubble constant? And by probe, we mean thing that we use to measure it. The cosmic microwave background radiation, supernova, quasars, or Cephids? Which probe is not used for the local measurement of the Hubble constant? Indeed, the cosmic microwave background radiation is not used for that. All the other things are used because they're all considered local by these crazy cosmologists who see things so far away that even the furthest things away are still local for them in the universe. So now, the next question, oh, we'll get the score. Oh, Leiden still striking a lead, nickname moving its way up though, so let's see how this keeps going. Third question, what are the two competing values of the Hubble constant mentioned in the talk you saw earlier today? 65 and 73, 66.2 and 73, 67.4 and 74.0, and 68.9 and 74.0. This really means, did you pay attention to that talk and really remember those numbers? Could this come down to a decimal place? We'll find out. There's still only about a 4-second gap between you and the real clock, so remember to answer before it says 4 seconds left. But you all did well done. And a lot of you paid attention. Indeed. 67.4 and 74.0, the two numbers that are very, very precisely measured and very, very different from each other. So we'll see what happens in the future of cosmology along those lines. How does that go in the scores? Leiden still topping the game. Nickname doing pretty well. Periton on a answer streak though. Zeus and the Rock still in there. And let's go. Everything still to play for as always. On question 4, which of the following scenarios is not a possible solution to the Hubble tension? A new theory of gravity, increase in dark energy density over time, exotic new particles, or a positive curvature of the universe? Which would not help solve this problem? Get those answers in. Yeah, positive curvature of the universe does not help. Really shows this is a nerdy quiz crew that is getting all these answers. But let's see who could do that fastest. Oh, nickname has overtaken Leiden. Leiden slips into second place. They're, I think, sitting in the Zoom pub, so they're probably a bit depressed behind me. I hope they're crying now, but we'll see. And we'll move into the next round of 4 questions. So those 4 were from the first talk, as you might recognize, the next 4 from the second talk you saw tonight. So let's see what we get. What do pulsars, FRBs, and RRATs have in common? All originate from a source less than a few hundred kilometers in size. They've all been seen to repeat themselves, all observed as short radio bursts, or all of the above answers. Answers are popping in. 2 teams to go. All people. Just guess by this point. It is indeed all of the above answers. They all originate from very small size, astronomically, all repeat, all observed as short radio bursts. See how that changed the leaderboard light and it's just descending downwards. So they better pick their game up. I wish I could see them a bit better on the screen because they don't look like they're crying, but maybe they are. So let's go with the next question in this round of how far away is the FRB of the same intensity but 4 million times brightness as a pulsar 1,000 light years away. This you might think you have to calculate, but I'm reliably told that the answers are so bizarrely far apart that you can just tell from which is the okay-ish answer of 1,000 light years, 2 million light years, 4 billion light years, or 100 meters. Everyone's scared of answering this question.
Repeat the question once more, Jay.
How far away is the FRB of the same intensity, but 4 million times the intrinsic brightness as a pulsar that is 1,000 light years away? Two million light years. 1,000 light years not far enough. 100 meters microwave oven could be reasonable, but they tend not to give the same kind of high frequency radio bursts unless you're particularly microwaving the same thing repeatedly in a very strange way. 4 billion light years, really, really far. 2 million light years, solid answer. See what that did to the score. Absolutely nothing. So let's see the next question. Number 7 of 12. This is a multi-select question. What is a Periton? Choose the things that it is. A winged deer that casts a shadow resembling a human. A brand of expensive wine. A dispersed, very short radio burst caused by opening a microwave early. Or a dispersed radio burst from outside our solar system. You can select more than one answer. Then remember to press submit after you've chosen them. Zoom Pub host was not happy about his answer to this question. But he already pressed submit. It's too late. That is right. It is a winged deer causing a shadow resembling a human and a dispersed very short radio burst caused by opening a microwave too early. Those are what a Periton is. How did that go? Nickname still doing well. Peritons themselves did not really move up a lot for that question, which, could have done better. Everything's still to play for. We'll see how this goes, though. On question 8, the last question in this second round. The FRBs are called fast because they travel at the speed of light, they last only for a few milliseconds. They are named after the Chinese fast telescope, or the microwave oven was thought to cause them, was used for fast food. You can do it. You can choose an answer. They are called fast because they are fast. They only last a few milliseconds. Were you fast? Wow. Nickname was. The leaderboard is not really moving up and down a lot at all. Nickname, good job for 8 right answers in a row and topping the list. So now we're going to move into the last round, which is nothing to do with either of the talks. So this is where everything is up to grabs. Everything has always been seen to change in the last round of our quiz every single time. So Get ready to answer these questions as quickly as you can to get the most points that you can. But whilst also being fast, you also have to be right. So let's go in round 3 for the final 4 questions. From what year is the first record of a supernova explosion? 185, 1054, 1479, or 1572? It was in 185. 1054 is very popular, as that was when the Chinese saw the Crab Nebula, but unfortunately it wasn't the first that was recorded, just the one that we care most about nowadays. So this probably mixed things up a little bit. Yeah, the rock came up over Zeus. Let's see what happens next in the final 3 questions. Everything is still to play for at the top, by the way. Everyone could overtake everyone. Which planet's transit in front of the Sun is more frequent? Choose now, Venus or Mercury. See in the picture the International Space Station transiting in front of the Sun. Not part of the question. It's a tough call, but it is Mercury has the most transits in front of the Sun. It's all a matter of angles and orbits and times and so many other things that it's very hard to guess, but Mercury is the most. Do they only ever happen in May or November? Fun fact. And so some little movements of points happen, but everything is still in play as we move to last but one question. In 2019, the discovery of 20 new moons of which planet made it the one with the most moons in the solar system? Jupiter, Neptune, Saturn, or Uranus? Indeed, Saturn. Well done, all of you that answered that question. Saturn now has the most moons currently that we've found, so we'll see what happens in the future as we can see more and more fainter things and look at them for longer. And now coming into the last question, how does the leaderboard look? It looks like it's still very close and could all be decided by the last question, which is Saturn has the most moons, 82, as we just said. Some have been lost and are being searched for. How many moons of Saturn are now being searched for? Faster answers get more points. Correct answers are the only ones that get points. So answer fast, answer right. And time is up. Indeed. We are searching for 5 lost moons of Saturn. So let's see what that did to the scores and then see the final score for the night. Please screenshot your phone if you're the winner so that we can give you your prizes. Leiden in 3rd place. Periton in 2nd place. And up there in 1st place, Nickname. So, hope you announce who you are. And I hope you all come to the Zoom pub afterwards and join us over there. I'm going to post now the link to the Zoom pub. So that you can come join us there. So in the YouTube, you can see the link in the description below, http://stem.oo/zoompub. And then you can join us in our pub online. And if you're watching anyone else, then please come join us there. As for now, the YouTube stream will end. I will see if I can find the background that points you to there, but I hope that you will come join us in the Zoom pub. I'll be over there too. See you later. Congratulations to the quiz winners, and thank you to all the speakers tonight.